Hello, today I'm going to talk about our work LLM Trainer, automated robotic data generation via demonstration augmentation using LLMs. This work seeks to generate robotic data by warping a small set of human demonstrations. We employ an LLM-based augmentation method to modify an existing demo to match new scene configurations. This process is divided into two steps. First, the LLM annotates the example demonstration, taking note of key time steps and relevant objects. Next, the environment is initialized to a new configuration, and this new scene, along with the annotated demo, are provided to the LLM. Using this information, the LLM modifies the recorded trajectory to reflect the new scene initialization. By rolling out these generated trajectories and saving the successes, we can create a set of demonstration that can be used to train imitation learning agents. Additionally, during the LLM annotation phase, we can optimize the demo annotation used by the LLM, significantly improving the data generation success rate. Thanks to this optimization, by the end of the data generation process, we have an optimized demo annotation that can be used to generate a fairly successful LLM-based feedforward policies to be used in addition to the trained imitation learning agent during inference. Additionally, we developed a simple ensembling method to combine our trained imitation learning agent with the LLM-based feedforward policy, taking advantage of the generalizability and long horizon planning of the LLM-based agent while using the trained imitation learning agent to provide feedback-based control critical for error correction. We evaluated our method on a series of simulation benchmarks and a mug cleanup hardware validation task. For the hardware task, the robot had to open a drawer, pick up a mug, place it in the drawer, and then close the drawer. Here we can see the LLM feedforward policy used for data generation, with the LLM modifying the recorded trajectory to adapt to the new location of the mug. On the right, we can see an example of when the LLM policy fails, getting stuck on the bottom of the handle. We collected 100 demonstrations using this method and trained an imitation learning agent. You can see the trained agent here. On the left, the trained agent is able to successfully complete the task, avoiding a collision between the mug and the handle. On the right, we see a failure, where the policy fails to grasp the mug properly, knocking it over. Finally, we combined the LLM feedforward agent with the trained feedforward agent. This ensembled agent is able to use the feedback policy to correct errors. So here we can see that the mug would have collided with the handle, but the feedback policy caught this error and told the robot to move around the handle instead. Afterwards, the feedforward policy resumed control, completing the task successfully.